Welcome to the tutorial session of Strategic Learning in Wireless Networks, Theory and Applications. During this tutorial session, we will try to go through again the concept taught during the first videos of Mehdi. We will try to revise the ideas. We will work on a couple of examples and try to digest these concepts. First, we will focus about the definition of a game in strategic form. A game is composed of three components. First one is the players. Players are the ones who make the decision in the games. Usually, sometimes they are called as agents as well. Then these players, they have to play certain actions. So they have a plan on playing certain actions. These plans are known as strategies. Individual player has certain set of plans, and altogether they have the entire action space that is defined for this game. Finally, when these players taking certain actions, they are rewarded. This is known as the utility or the payoff. One thing you have to understand here, when a certain player plays one action, the rest of players have their own set of actions. Usually in this discussion, we denote it by this -n notation. When a player tries to improve its own rewards, sometimes the actions of other players might be conflicting with each other. This confliction among these actions and the strategies leads to a certain competition among them. So individually or as a together, they try to take their try to plan their actions to improve their rewards. This could result in a conflict among each other, which would leading a competition among one another. That is why this is called a game. There are two types of players. We are going to focus in this course. First one are the rational players. The second are the irrational players. So who are the rational players? So rational players are fully aware about all possible choices that they can make, and they try to predict or make some expectations on unknown things. Then what they try to do, they pick a strategy that ensures kind of optimality. So that ensure the maximum reward or minimum cost. Then on the other hand, we have these irrational players. Although they are fully aware about all the possible choices, sometimes they tend to do things differently. For example, in the Matrix movie, Neo, he had two options once. So he had to save his girlfriend, but doing the humanity will cease to exist. The other option, let his girlfriend die, and he can help to build up the humanity. The ideal solution as a rational player would be, he would wait, okay, whether to save the girlfriend, what would be the payoff, or let the girlfriend die and save the humanity, what could be the payoff. Depending on that, he will pick what is the best. But in his case, what Neo did as a rational player, he decided to save the girlfriend, thinking probably he could save the humanity later on. So usually with rational players, it is somewhat easy to analyze what would happen under certain circumstances. With irrational players, it is quite difficult to predict what the player would play. Luckily, in this course, we will be focused on rational players. Okay, for start, let's try to play a simple game. This I call it as Mayor's Big Heart. So there's a mayor who wants to pass certain constitution rule or plan or some project. So he decided to freely give away maybe $1,000 of money. So he needs votes or support from the panel. So what he says, voting for his new proposal allow people to eligible for this reward. However, there's a small catch, with politicians, right? So you must compete with one another to get this money. In order to that, everybody has to place a bid. Or in here, we can formally in mathematics say, we can say they have to pick a certain integer from 1 to 1000. Once they place this bid, what Mayor will do, he will pick the maximum bid out of everybody. And those who pick this maximum value will be the ones who are rewarded. Suppose there are n winners. So the n number of people that have placed the maximum bid, then the individual reward is given by 1000 divided by n times x. The rest of the money he is going to keep it with himself. Okay, now I guess the picture is clear. There's a reward of 1000. Everybody has to pick a value in between 1 and 1000, an integer value in between 1 and 1000, and the ones who pick the maximum value will be rewarded, and the reward will be defined by 1000 divided by n times x. Now go ahead, make your bid and make sure you win. This would have been a really nice game if we could have interacted together. However, we are not going to do it right now. Therefore, I'm going to assume there are two different players and try to work this out for you. Let's suppose this is you and you make kind of a random guess. What you need to know, you pick a small value, of course, then what you're going to get will be large, right? Because as your x hat becomes larger, the reward is going to be small. But there's a risk. If you pick small x, there's somebody who's going to pick a higher value and you will be a loser. Let's say, for example, if somebody decide to pick 1, say this is x hat, or rather it should be xn. If he wins, the reward would be 1000. Okay, I'm just assuming now n is equal to 1, which is not ideal, but let's say right now. If he picks 10, then the reward will be 100. Basically, the benefit is you go for lowest x. Disadvantage, if n is larger than 1, there's a chance somebody is going to overthrow you. So let's see if you have already picked something other than 1000. So let's say you have picked 10. Most likely, somebody might have picked 11 and you are the loser. If you pick, in order to overcome this guy, if you know he's going to pick 11, you are going to pick 12, there's a chance he might is going to pick 13. Likewise, this would happen again and again, until you go to the bid of 1000. If you don't place this, there is a chance somebody might outsmart you. But what happened with this? Let's say if you have, like, for example, 2 players, A and B. In order to defeat B, you are placing this bid because you don't know what B is going to bid. And at the same time, B thinks in the same way because we are now thinking about the rational case, right? So B is also thinking, okay, if I place a certain bid, A might place something larger than that. I'm going to go home with nothing, still voting, but nothing. So he's going to increase his bid. So basically, he's going to end up with a bid of 1000, hoping, okay, If he has placed 999 and still I'll go home with $1, which is not big, but at least it's a reward larger than zero, right? So eventually they reach to this conclusion. A decided to place a bid of 1,000, B decided to place a bid of 1,000. So basically there are two winners now. So what is the reward? It would be $0.5, right? For each of them. Then what is left with the mayor? Yes, $999 with him. So basically he has spent $1 to get the what he needs from you. Now suppose if there were like n players instead of 2 players. So basically everybody or individually they will get this value. Sorry, this should be 1,000, not 10,000. And there are n winners. So basically still this goes to $1, right? That means with this approach, whatever happens, if players are rational, mayor will only give $1 to pass, get the vote from all the members. Pretty nice, right? So now let's take this game into a different level. Now think that you can discuss with each other and allow to place a bit, which is not going to happen with the way, but let's say this is a hypothetical case. You can coordinate with one another. Then you come to certain agreement. If that happens, what could be the best bid? Now go back. Let's go back to these two users or two players. Now what you need to do, you need to have the maximum reward you can get without losing. So basically you two agree. So which means if you want to have the maximum reward, mayor should go with empty-handed, maybe in terms of money, right? So basically what you need to have, so you have these 1,000 of reward and you have 10 players facing the maximum bid, and if you multiply with, because this is per one person, right? If you multiply with all n, you're going to end up with, okay, this is the amount, the total amount that you're that mayor has to pay for all the agents. If you want to take all the money from the mayor, this quantity should be equal to 1,000. That means everybody should agree to place a bid of $1. If everybody does it, let's say in two users example, if both A and B place a bid of 1, each of them will receive $500 compared to the $1 case when there was no agreement, right? This is a big win. You know, suppose we have n players and we play this game, and if that happens, everybody plays a bid of $1. An individual person would be awarded this amount of dollars. Now, suppose there's one guy in that in group thinks somewhat different like this. Okay, now I'm going to get this much. What happen if I place bid of 2, although we agree to place bid that equals to 1? If that happens, x hat would be 2 and number of winners will be 1, right? Basically, that means this person is going to get a reward of 1000 divided by 2. It means $500. So unless n is equal to 2, I mean this n here I was talking about the total agents. This 500 is quite large compared to 1000 of n. So that is why even though people make certain agreements, unless they can trust each other, they always go back to here, right? So the communication matters as long as they can come to certain agreement and they trust each other. A nice example, right? Okay. Now let's talk about a concept, the best response. So it is a strategy or set of strategies that produce the most favorable outcome, highest reward or the lowest cost for a certain player, given other players' strategies. Formally, we can present it as like this. So this is the utility and the certain strategy selected by player N that maximize his utility is the best response. So in other words, we can say there exists a certain strategy that provides a payoff that is either equal or higher than all other payoff that that player get by playing all different strategies. So now let's consider a simple example of this rock, scissors, paper game. So ideally, the concept behind this game is players have to pick one out of these three options, and they are competing with two other players. So basically, if two players pick the same choice, there is no winner. However, if they have different choices, one could beat the another based on this figure. So rock beats the scissor, scissor beats the paper, and paper beats the rock. That simple idea alone explains what is best response. So the best response for the strategy of playing scissor by the other player would be playing rock, right? If the other player plays takes the strategy of playing paper, what we have to play is scissors. Similarly, if other player plays the rock, the best response is playing paper. Pretty simple and clear idea. We'll just try to digest this idea. Then let's take another example. So we present the strategy and reward in a tabular form. And here player A has two different actions, B has two different actions. For each action, they get a different type of rewards, which are shown in here. So the first one show the value of the reward received for the player A, and the second tuple is about the reward for the player B. Now, what could be the best response? Given B plays action 1. So B plays action 1. So basically, we are not interested on this part, right? Now A has two actions. You can see if A plays action 1, he will be rewarded 3. If he plays action 2, he will be rewarded by 2. Since A is interested of increasing its reward, so this is the point we are interested in. So basically, he has to play action 1. You can play with different things. You can consider about, okay, now if what happened, B plays action 2, and what if A plays action 1, what is the best response of B? You can check all these combination in here. Okay, let's check another example. So let A1 and A2 be advertising costs of two different firms, and the profit of firm 1 given the advertising cost of firm 2 is given by this expression. So we know A2 is the advertising cost of firm 2, it is given, and here the C is a constant, and P1 is the profit. So the question is, what is the best response of firm 1? So now if you think the profit is equal to A1 C plus A2 minus A1. Basically, we can write it as alpha into A1 minus A1 square. So what we are looking is to maximize P, right? So basically, we can go for this as minus A1 minus alpha over 2 square. Would it be, yes, minus, it would be alpha square over 4, right? If I am right. Then, if you want to maximize P, maximum P should come happen when this part is equal to 0. It means it will be alpha square over 4, which is achieved when A1 is equal to alpha divided by 2. So in here, this is right. This says if the firm 1 knows the advertising cost of firm 2, this would be the best value he has to spend on advertising that maximize his profit. You can simply check for the cost for, or the best advertising cost for firm 2 following the same equation, and you will end up with a similar result. Okay, now let's work on some exercises. I would recommend you to pause the video, go through the problem and try to solve it by yourself and see whether you can, then you can validate it with me. So here we are going to go back to this Mayer's big heart problem. Just reminding, the reward per person is this, where the maximum bid is X hat and the number of winners are N, not the total players. Now what the question is, okay, we have to check in terms of player 1, what is the bid he has to place, knowing that the maximum bid and the number of players that has played this bid. So he need to find the best response. So there are two options. Option 1, he can pick the same bid, right? That would give this much of reward. The other option would be he has to put like a bid just slightly larger than X hat, because the reason is higher the bid, lower the reward, right? Even though you win, which ends up of a reward of X hat plus 1, because now you are the only winner. Oh, okay, the player 1 is the only winner. Now let's see, okay, when this become better than having the same bid as the others. Now if we go check this scenario, and plus 1 into X hat, right? Okay, these two cancel out. So we are here with X hat, power X hat plus 1 should be larger than this 1, right? So now if we deduct here, it would be X hat 1 over n, right? Yes. This says under this condition, placing a bit that is slightly larger than others is beneficial. Now we know n is either 1 or larger than 1, integer number of players. So it means this is going to be either 1 or a fraction, right? So basically we can say x hat is larger than or equal to 1, because we know for all these choices of n, these are going to be a fraction and x hat is an integer. So basically this is what is going to happen. So which we can conclude that, okay, whenever we know there's a bit placed, what we have, in order to play a 1 to win, he has to always go for this option. So he has to always bid something larger than this, unless this x hat is 1000, because then only he can play 1000 and it is going to be divided among everybody. $1 is going to be divided among everybody. So I think we came to same conclusion earlier without introducing the concept of best response, but this is just a validation. Okay, now it is time for you again. Pause the video and try to work out yourself and see whether you can find these best responses. The question is, there are 3 workers, A, B, and C. They would like to demand for a raise for everybody by 2 units of their salary. So there is an increase of 2. However, the question is, okay, whoever that's going to make a demand going to lose 1 unit of his own salary, despite of whether the employer is willing to give a raise, because the approval of raise happens only at least there should be 2 demands. So 2 different workers have to make demands. Now the question is, what is A's best response when both B and C already demanded for a raise, when both B and C decided not to make a demand and only one of them make a demand? So in order to analyze this scenario, let's try to go for this. We can go for a tree view or kind of a tabular view of try to find out what are the possibilities. But now we'll, instead of going through all these tabulars, let's pick these specific choices. Since we know both B and C already demanded for a raise, so B made a request by sacrificing 1 unit of his salary. C made a request, and he then employer has to approve it. Now A has 2 options: demand or not demand. Since both B and C already make the demand and employer agreed to increase the salary, if he, even though he didn't like request, he's already getting this +2, right? Because already other 2 have made the request. Say he, even after both B and C make the demand, if he again make the demand to the employer, he will cut 1 unit out of his salary and he is going to end up with increase of only by 1. So under this scenario, it's the case 1, when B and C already make the demand, this would be the best response of all. So not to make any demand. Now let's go for the case 2. So B and C picked not to make a request to for a salary raise. So now A has two options: demand, not demand. Now, if he demand, he's going to lose one. And since only there's one request, there is no salary increase. So basically, he ended up with -1 reward. Or we can say his salary is going to decrease because he asked for more. But if he decide not to make a request, he's not gaining something and he's not losing something. Basically, in this case, it is better not to request. So when he knows other two has not made any request, it is better him to not to make any other request, right? The last case, BOC already make a demand. Now let's focus about the two choices of A. Since there is already one demand, okay, now suppose, okay, now A make a demand, so that means he's going to lose one of his salary. Since one of the others have already make a demand, employer will agree to increase. So basically, he will all will get +2 for their salary. So basically, he end up with +1. If he is not going to make a demand, he is not going to lose anything, and there will be no raise for everybody. He is going to end up with no change. So in this case, the best response will be making a demand. So you can see, depending on other players' choices, the best response changes, right? Now let's talk about a solution concept, Nash equilibrium. So this is defined for non-cooperative games involving 2 or more players. So here each player is assumed to know the equilibrium strategies of the other players. So basically that means the strategies that the other players are not going to change. Why? Because there is no gain by changing their own strategy. So under these conditions, the strategies that all the players have been selected and the corresponding payoffs constitute a Nash equilibrium. However, the existence of such a equilibrium and the uniqueness of the equilibrium, we cannot make any guarantees on that. So formally, we can represent it as like this. So if you consider all the players and for all their strategies, they need to satisfy these conditions. That means deviating from the best response or the deviating from the strategy always result either equal or lower payoff. So if that happens to every users at the same time, the set of strategies for all the users and their corresponding payoffs together constitutes a Nash equilibrium. Now let's try to see a couple of examples and try to understand what this means. For example, let's say this rock, scissors, paper game among 2 players. In order to identify what are the benefits, losses, the payoffs, the strategies, let's try to go for the tabular form in this case. So let's consider there are 2 players playing this game: rock, paper, scissors, rock, paper, scissors. So let's say winning equals 1, lose meaning equals -1, draw, because that can happen here, makes 0. Now we know in terms of player A and B, when they play the same, make the same choices, it will be a draw, right? So they will get 0s. 0 reward for playing the same action at the same time. Now let's say B plays rock and A plays paper, it means he's going to get 1 while B is going to -1. If it is other way, if A played scissor while the B plays rock, he is going to lose and B is going to win. So you can see only the sum of the rewards added up to 0. Usually this is called this a zero sum game. So if somebody wins, the other will be losing the same amount. So now if you think about this case, A plays rocks and B plays paper, so B wins while A loses. So if we follow this strategy, at this point, it would be like this, and here, when A plays rook and B plays scissor, A wins and B loses. So in this case, A loses, B wins. Somewhat a balanced game, right? Now let's try to find what is the Nash equilibrium here. So Nash equilibrium means, okay, you can't deviate. By deviating, you are not going to gain anything. Now let's think about this part. If let's say at this strategy and see whether A has incentive to deviate. Yes, of course, if we in this point, A can always select to play paper. And even at this point, B always going to select paper, right? So basically, this is not an equilibrium point because both of the players have incentive to deviate. Now, if we go for here, A doesn't want to change, but of course, B would prefer to change because he has -1 here. For any other choices would be beneficial for him, right? Similarly, if we go here, okay, here it says A would prefer to deviate while B does not. So the same thing would happen in each of these cases. You can go through everything, every possible choices, and they would find at each these choices, either A or either B prefer to deviate the strategy to improve their utility. So basically, there is no agreement or kind of a stability among these choices. So in this example, you can say the Nash equilibrium does not exist. Let's go for the example 2, which is the same example I used in the earlier case. Now let's try to find the Nash equilibrium. Let's start from this point. Okay, at least we can see A does not want to deviate because choosing action 2 will make him lose, right? So basically he doesn't want to change. And B, either he play action 1 or action 2, he's going to end up with the same value. So basically they can, at least B might stay here, might deviate, but there's a chance he might stay here because there's no difference of moving to action 2. Now, if we consider about this scenario, of course, A is not going to stick with this action 2 because he knows action 1 is most beneficial. Now, if we consider this case, A is getting a reward of 1, but a change in the action, he would get a reward of 2. Basically, this setting, A is not going to stick with action 1. So we don't need to worry about what B would play, right? So now if you think about this one, A would like to stay here, and B, he doesn't want to be here, right? Because changing action 2 to action 1, he would get a much benefit. So he won't happy to stay in this one. So in this case, at least you can see there's a one strategy set that could generate a scenario where the payoff of 1 doesn't change or payoff 2 doesn't change. So this is the Nash equilibrium in this example. Now if we consider about the advertising cost and the profit based example. At least let's see whether we need the previous solutions and to see. And we know, okay, the profit of one, we ended up with equation as I can remember, it was C plus A2 square divided by 4 minus A1 minus C plus A2 divided by 2 square. Right, yeah, this is the profit. So whatever A2's choice, A1 try to reach, try to make this equal to 0 in order to maximize its reward, right? So basically, if A2 has a certain choice, A1 will always pick C plus A2 divided by 2 because this is the best response that the firm 1 can have. Similarly, if we use the same equation for the firm 2, for a choice of advertising cost at firm 1, firm 2 will pick this as his best response. Now, if we can have a scenario of values for A1 and A2 that satisfy both of these equations, then it means neither of firms would prefer to deviate from one another, right? So if we now what we need to do is we need to solve these two equations. So we have 2A1 minus A2 equal to C from here, and from here we have, so I'll put like this, A1 minus, sorry, plus 2A2 is equal to C, right? So if you multiply this by 2 and add it, then we have 4A2 minus means 3A2, and okay, we ended up with like this, right? So I think this is going to be the same for A1 as well. So that means if firm 1 and 2 decide to use C as their advertising cost, neither of firms would gain by deviating from it. So basically, this is the strategy they have to pick, and the payoffs would be identical in this case because, okay, this would cancel out C square, right? So these two combinations together constitute the Nash equilibrium in this example. Okay, now let's check another example, sorry, exercise. I recommend you to pause your video and try to work yourself, then come back again. And reminding again the reward given the maximum bid and the number of winners. So the target is now you have to find the Nash equilibrium when the number of winners are larger than 1. Now if you consider about two cases where sticking with the same bid versus selecting a bit slightly larger than the current one, which yielding this payoff. So in order to find equilibrium, we have to consider the cases, these three cases. When this happen, when sticking with x hat would be the beneficial, and when, okay, deviating from it is beneficial. If we consider the simplification of this would be, so I'm going to keep this as it is, just to make sure nothing goes weird. So we have 1 over 1 plus 1 over x hat means, okay, we can go like this. Now I'm just changing here. So we have, right, this is the condition we ended up here. Okay, that says in order to okay, we can consider about like, okay, this part, this symbol. So when sticking with the original x hat would be the beneficial. So that means this condition. This is achieved when x hat is, yes, the top one is less than 1 over n minus 1. Since we know n minus 1 is a positive integer, this part is going to be a fraction, which means x hat should be less than 1, which is a contradiction. We never achieve this scenario. So basically it means sticking with the original bid is never going to be the best case. So remember, just a reminder that, okay, we consider x hat is less than 1000. Of course, when it is 1000, we have to stick with. So basically that means we always need to pick this one. That means we always need to pick the bid like this. So eventually this convergence comes when we have this equality condition. When x hat is 1000, then nobody want to deviate from here, from that strategy. So basically that is where the Nash equilibrium achieves. So it means x1 to xn would be 1000. That is the action. The reward would be, let's say there are n players, so okay, we can just say 1 over n plus 1. This is the reward. So these two constitute the Nash equilibrium. Now if you think about the other example about the demanding for arrays. So in order to find this, somewhat it would be better to have a tabular form or tree form. I prefer the tabular form. Then let's say we have, okay, A, B, and C. It is a challenge here. So what we do, we will keep like this. So we keep two tables. And we have both A and B here. This is a demand on demanding. It is same for this. However, for that here we consider C is demanding. This one C is not demanding. By doing that, we have the third axis, which ideally would be written in this way. So this is A, B, and C. Instead of that, we just write in our two tabulars that could align in this axis. So now if you think about, okay, here two of them are demanding, A and B, so they only get arrays of 1 because of the demand. They are going to lose. And okay, yeah, Z is also demanding, so he's only getting this. Now if you consider this case, only 1 is demanding. Since this guy is demanding, all are getting the raise. So here A only gets 1, B gets 2, C gets 1. Similarly, here A gets 2, B gets 1, and C gets 1. And since here, two of them are not demanding, only just one. So this guy doesn't get anything and this guy is going to lose, right? Now, if you think about the same case, now this guy is not demanding, but these two are demanding. So basically, they will get 1 and C is going to get 2 because he's not losing anything, just gaining. So in here, so these are like D and D, D and D. And here we can consider at this phase, 2 of them are not demanding. So there is no race. Yes, of course, since this guy is not requesting anything, C is always gaining nothing. And B is demanding, he's going to lose. A is not demanding, A is demanding, and B is not demanding. And finally, nobody demands, nothing changes. I have a neutral. Now, if you think about the Nash equilibrium, let's start somewhere here. Now it is a bit challenging. We have to think about jumping between tables. But of course, we can just reject one strategy if somebody decide to deviate from here. Like if you think about here, A is trying to deviate, right? So basically, this is not going to be a Nash equilibrium. So if somebody is here, let's see, A is not going to change anything. 2 is not, B is not going to change anything. Let's see. Okay, that is okay. This matches with this one. C is not going to change anything. So this one seems to be a Nash equilibrium. Now if you go here, A doesn't want to change. B, no. C, no. This is a good one. And if you think about this one, of course, C is going to change from here to here. So basically, this is not going to Nash. If you think about the logic behind the others, I think this is going to be a Nash equilibrium. And of course, these are not good because here you can easily deviate. Let's say C can easily change here, or B can even change from here. So basically, these two are not going to be Nash. But how about this one? This is going to be pretty interesting, right? See? Okay, changing for B. Okay, he doesn't like to change because he's going to lose. Let's say A. No, he doesn't. He won't change. Okay, here. C. He won't change. So this is another Nash. So in this case, we have 3 solutions. One at here, one at here, one at here. So naturally, what could happen? I would say naturally, it's tend to happen here because nobody willing to take the risk. Because taking a risk while others won't support, then definitely you are losing. So we're here. So if they want to improve, at least they need to kind of have a coordination and trust. So these are the strategies and corresponding payoffs. So there we can see 1, 2, 3, 4 Nash equilibria. Okay, now let's move to another concept, dominant strategy and the equilibrium. So what is a dominant strategy? So it is a strategy that is better than any other strategy for a given player. Yes, of course we are talking about a given player. No matter how others play. So whatever the others do, if some strategy is supposed to provide the best outcome, it become the dominant strategy. So players used to play that strategy regardless what others do. So there's like a 2 kind of definition. So if strategy 1 is always better than any strategy 2, disregarding whatever the opponent's strategy is, we say strategy 1 dominates strategy 2, right? Okay, then if the strategy 1 is either better than or equal to the strategy 2, then we say it is weakly dominating. So strictly dominating means, of course, we definitely know it is better. Weak dominates means it could be either better or equal. So the strategy that dominates all other strategies known as the dominant strategy, right? Then if there is a dominant strategy, then most likely players are willing to take that strategy. Then the nice important aspect is here, right? Okay, with the Nash. If there exists a dominant strategy, so it is at a Nash equilibrium. The other important aspect is if all players have dominant strategies together, then there exists a unique Nash equilibrium. Now let's check a couple of examples regarding this concept. So find the dominant strategy for A, B, and all the ones that couples together, right? So we know if you think about player A, so if B plays action 1, we can see this is action 1 dominates action 2, right? But if B plays action 2, then action 2 dominates action 1. So in that case, A doesn't have a dominant strategy unless B sticks with 1. Now let's check from the B side. We can't make a claim at this point, right? Let's now we have to check from the perspective of B. We can see here. See, when A plays action 1, B can either decide to pick action 1 or action 2. So basically, these two actions are kind of weakly dominating one another. But now if we think about the action 2, when A plays action 2, it is clear that playing action 1 is beneficial, right? So that means since this has like a weakly dominating aspect, and here it has a strictly dominating action 1 strictly dominates in the action 2, we prefer to stick here because whatever A plays, either he gets 2 or 3, nothing less than that. Now we know B is going to stick with this. So if B is going to stick with this, what is A going to do? He's going to pick this one, right? Because that is where the A gets most. So the dominant strategy is A playing action 1 and B playing action 1. Okay, maybe another example. So here we consider about like two different bars. They can decide to sell their beer for 3 different prices. And okay, let's see these numbers. So okay, they are expected 6,000 beers per month consumed by tourists, and they choose the 2 bars randomly. So roughly we can consider 3,000 will go to bar A, let's say bar A, and 3,000 will go to bar B. And there are 4,000 beers are expected to sold for natives. Okay, they pick the bar with the lowest price. If the price is same, they split even. Okay, now let's try to put this in a tabular form to analyze. So A and B, A can decide to sell for price 2, 4, or 5. Similarly, we can consider the same 3 options, right? Now, although it is in thousands, maybe I'll just drop thousands which is easier to write here. So we know roughly half of these tourists are going to visit here. So basically it means like 3 units are going to allocate it for both of them. This is the constant part. Then out of 4, it can be 4004 or 22. That is how the this much of let's say customers are going to be split over the choices of the selling prices. Okay, which is okay if the price is equal, they get even number of tourists, even number of natives. So it is 5. So both are getting 10 and 10 in thousands, right? So here, okay, at least I'll just not get 3 to 5 here, 5. So if they get 5,000, if this price is same, they get 20, 20, or 25, 25. Okay, now comes the interesting parts. Okay, now A has a high price. So basically he's losing all the natives, just he has to rely on tourists. Where B get half of the tourists plus all the natives, 7. So it's 2014. So it's going to flip. Yeah, yes, because it is symmetric. So if you go here, it is going to be 15 and 7 into 2, 14. Yeah, like that. So maybe we can go 14, 15, right? Yes. Now if we consider about this case, he will get only tourists here, while this guy gets tourist plus native. It is 28, so it's going to flip in here. Yeah, pretty interesting numbers, right? Okay, now we have to find the dominant strategy. Clearly, this is not going to work because both can improve, right? Okay, so okay, the question is, okay, which option dominates the others? Okay, yes, of course, B is not going to stick with this one, right? We can improve it. Disregarding what A place, we can improve. So it's not going to stick in here. Now, if you think about, so basically, B is not going to stick with the price 2. So he is not going to stick with here because moving 2 to 4 is always giving him better outcome. Similarly, A is not going to stick with 2 because, okay, every time he moving from 2 to 4, there's an improvement. So A is not going to play this, B is not going to use this value. Now we can just focus about this region because others won't happen. At least they are not profitable. If you think about here, if this is 2020, what could happen? We would not deviate, right? Because it is going to lose. And A would not deviate because it is going to lose. So B is going to stick with here. Why? Because, okay, now I think we need to consider it as a different way. Like, okay, 20 is always better than 15, as 20 is always better than 25. That is how. So basically, B finds, okay, it is better to stick here because whatever the choices of A, I'm going to benefit. I'm going to benefit compared to moving to 5. So of course, if B A is playing 4, and then I could have played no, okay, that means yeah. Of course, if they agree, they could have here, but of course, since there is no agreement, this action seems to be best for B. Similarly, for A, 15 is lower than 25, 20, 25 is lower than 28. So basically, he's also picking this one. So they are going to end up in this case. Right? So this is the dominant strategy. Let's check another solution concept, which is known as Pareto efficient solution. So in this solution, one cannot improve its payoff without causing losses to others. Unlike Nash equilibrium, where they don't care about what happened to others, right? So these kind of Pareto efficient solutions, there can be several Pareto efficient solutions in a given problem. And one thing we need to add, it does not guarantee the fairness. So it doesn't guarantee that all the users are going to have kind of like a fair kind of reward. So formally, if we pose the Pareto efficient requirement, if a strategy is a Pareto efficient, that means there is no other strategy that allows a user to improve their utility without causing a loss of reward for any other user. So this is a Pareto strategy. There is no other strategy that helps to improve its own reward without losing the reward of any other player. What is the challenges in this Pareto efficient solution is since there can be multiple solutions, what solution we have to pick? That is a challenge. Okay, how to pick a certain Pareto efficient solution. Then the other challenge is this Pareto solution efficient might not be stable, mainly because of this, because there will be certain strategies that allow certain users to improve reward by that could lose the payoff of the others. Okay, let's check one example. So in this example, the question is find the Pareto efficient solutions. So the payoffs are given in the tabular form. In order to find whether each combination of these actions, which make the joint strategy is a Pareto efficient, we have to check each individual strategy and see whether they satisfy the Pareto efficient conditions. Now, if we consider about this scenario, now let's think in terms of player A. Right now we can see the payoff 3 is the maximum payoff that player A can achieve in this scenario. So of course, then there is no intention of player A to deviate from this action. Therefore, let's check from the perspective of player B. Here he has the payoff of 2, and if he changed his action from action 1 to 2, he cannot achieve a higher payoff. In this regard, neither of these players can deviate from this action, and nobody is going to deviate from action in order to improve their gain. So basically, this satisfies the Pareto efficient condition. So this is one Pareto efficient solution. But if we go to action number 2, you can see player A can improve by changing from action 2 to action 1. However, by doing that, player B is going to suffer. Based on the definition of Pareto efficiency, a player can change their action, change their strategy to improve the utility, but they should not result a loss of utility for any other player. So in this case, deviating from this action could result a loss of payoff for the player B. Therefore, player A cannot deviate from this strategy. Similarly, we can see player B, of course, he is not going to change because there is no gain for him. So we can consider this as another Pareto efficient solution. Now, if we consider about this setup, by moving, okay, now, yeah, first we will check from the player A, then we will go for player B, right? From player A, if we change from action 1 to 2, it could improve, but it will decrease players B's payoff. Therefore, it is not allowed to do so. From player B's perspective, changing from action 2 to action 1, okay, at least it doesn't change. However, by changing that, it could improve player A's payoff. Therefore, more tendency is to move instead of playing action 2. It is more tendency is to move towards playing action 1. Therefore, this is not considered as a Pareto efficient solution. And the last, let's go to this one. Of course, player A doesn't want to change his action. And here, player B, if we change from action 2 to action 1, yes, of course, we can see there's a gain. And player is not going to suffer. Therefore, there is a tendency that player B is going to move from action 2 to 1 because it doesn't affect player A. Therefore, this is not going to be stable scenario. So this is going to be a Pareto inefficient solution. So in this case, Pareto efficient solutions are these two combinations. Now, if you think about this case, given this is the payoff per any person who has already picked their bid as equal to X. So now suppose there's a one player N, right? Now let's see whether he would like to change his decision. Suppose his bid Xn is less than X, which is this one, right? In this case, his payoff is 0 because he didn't bid the maximum value. Then what he can do, he can change his strategy. So he can change this Xn value to X. However, by doing so, what could happen? By doing it, there will be another new winner, right? Then the total winners are going to change from N to N plus 1. Okay, we could say it is being changed N to N plus 1, which means the payoff is per person is going to be like this, which that means individual person is going to suffer, like all other winners are going to suffer by doing it. So basically, if a player has already selected a strategy that is the bid that is not going to the maximum one, if he is decide to change his bid to the maximum bid, then others are going to lose their utility, right? Then okay, by doing it is not going to be like changing it. So changing Xn to X is not allowed. In that case, sticking with the original choice is Pareto efficient. You can see, but this is not the optimal, but like this is not the optimal result. Like there are people who are suffer, but still this is Pareto efficient. Now consider about a guy who is already has the bit xn is equal to x. Now let's see whether he prefer to go for something like this, x plus 1. By doing so, all other players will get a payoff of 0, which means changing the strategy to improve its own utility cause a loss of utility for other players, so this is not allowed. So basically this says whatever the choices they made, whatever the choices the winners has made, they are Pareto efficient. They can't change. They can't deviate without causing trouble to others. Now, if you think about this case, but this xn is less than x, and he is decided to go from xn to xn dash, which is still less than x. So basically, by doing it, okay, this person n, he is still not going to gain anything, and others are not going to lose anything. So basically this strategy is allowed, right? This change is allowed in that case. So original choice of xn and the other choice of x. So this scenario, because now if you can think about that, so winners, they have picked x, nth player, he has xn, and some other losers, they have, let's say, x hat minus. Now what we did, we changed this xn to xn dash, which is still less than x, and still overall payoffs have been not changed. So basically it means we can move from this strategy to this one without causing any loss to any other. That means we are not strict to stay in this strategy. So basically it means this is not Pareto efficient. So we can move here. So what is the maximum value that x dash n can get? It should be x minus 1, right? Increasing beyond x minus 1 could result in this scenario, which is then it becomes a Pareto inefficient. So basically any result, any scenario where winners having the bid x and all the losers having bid x minus 1. Say this is all winners. Of course, this is the requirement, and this is all losers x minus 1. These are the Pareto efficient solutions. All others are Pareto inefficient. Okay. Now let's move to another strategy, the mixed strategy. So previously we consider about strategies, although we didn't mention, they were we usually refer them as pure strategies. So we have certain two different strategies, either we play one or the other, like there is no nothing in between them. Now we can consider this mixed strategy as playing something, a combination of those two specific strategies. Ideally it is unfair to say a person play a mixed strategy, but if you think we play a game repeatedly several times, a player can decide whether to use a certain strategy for several times, while there are some other strategies in other times. So in that case we can consider it as a probabilistic approach of choosing his strategies. So that means the mixed strategy is an assignment of probability for each pure strategy. So basically, that what player will do, they will start to randomize their pure strategies and try to improve their utility. With this introduction, yeah, we need to consider about a probabilistic choice of each strategy. So in that case, we introduce this probabilistic choice pi. So the player n has, let's say, s number of different strategies. So this probability says what is the probability of choosing his strategy I. That is what we call the mixed strategy. With this conversion or with this choice of randomizing pure strategies, we can convert the originally there was like a finite number of strategies. If you consider about the simple example of having this tabular form, yeah, we had A and B, and he had like two different actions. So if when player A is allowed to randomize these two strategies based on the probabilities that player assign, he could create infinite number of combinations out of these two strategies. So basically that means it converts the finite strategies into infinite number of strategies. So basically we can simply say action number 1 and we have action number 2. What we do, we assign alpha 1 minus alpha probability here. So the choice of alpha is going to be in between 0 and 1. So with this in this domain, we can have infinite number of choices for alpha. Means we have infinite number of possibilities of mixing these strategies. Now we need to check how we calculate the payoff. Previously, we knew for given one strategy and the strategy of others, there was a payoff specifically defined. Since now both players, or if we have more than two players, there are multiple players, they start to randomize their strategies. We have to consider a payoff in terms of these random choices. So here what we do, similar to calculating the strategies, we could use the same idea to calculate the payoff as well. So the probability of playing a certain strategy and the expected utility. Because why this is an expected utility? The reason the other players, they also randomize their strategies. So this is our choice of strategy, right? But this is the choice of all the others. But this choice again based on certain probabilities. So we take the expectation of over these choices, and this phi minus n represent the marginal distribution of the strategy is the probabilistic strategies taken by all other players. So this roughly says the expected payoff for playing action I. Then we take the mean over all the possible actions, and it results the payoff of the user n. Nice thing in this mixed strategy is like, okay, if we have finite players with finite number of pure strategies. So finite players, finite number of pure strategies. Originally we said there is no guaranteed of Nash equilibrium, right, with the pure strategies. But now if we introduce a mixed strategies on top of this scenario, John Nash has a paper proving that there is at least one Nash equilibrium that can be found using mixed strategies. This is kind of a powerful result. Let's consider one example. So here you can see about like two transmitters having access to two different channels, P and Q. The orthogonal access reward two differently or when accessing those two channels. And when they're sharing, they get different rewards for accessing the different channels. If you try to go for the tabular form of this one, say we have transmitter A and B accessing P and Q. Right. Now if you consider about orthogonal access, reward of R over P. So whoever accessing P gets R and whoever accessing Q gets 2R. Then when sharing, channel P yields reward of R and channel Q yields reward R by 2. Find pure strategy Nash. Okay. If we are here, definitely A prefer to move. And if we are here, of course, B doesn't want to move. So this is one of them. And similarly, this one should be one of them due to symmetry, but this one, of course, it is not. So two different strategies, PQ, QP, sorry, not RP, and corresponding payoffs constitutes Nash equilibriums in pure strategies. Then what about Pareto optimality? Yes, here we can change without causing any losses for others. Move here, no losses for others. So this is not going to be a efficient solution. And so if you consider here, changing doesn't improve for A, changing doesn't improve for B. So they are going to stick in here. Same goes here. So these are Pareto efficient. How about this one? Yes, changing improves others, so he's not going to stay here. So similarly, these two are Pareto optimal as well. Now, if you go for mixed NE, let's consider B is using this strategy with probability alpha. So this one with 1 minus alpha. Now, if we consider about the utility, when A use action P. Since he is randomizing these two actions with probability alpha, he will be rewarded R amount when we is playing this, that means with alpha probability, and R probability when we is playing this with 1 minus alpha. So basically his reward is R, right? When he using channel Q, is receiving 2R of reward with probability alpha, but R over 2 reward with 1 minus alpha. So he will be rewarded half. It is like, yeah, this is half. Okay, 3 alpha. Why not good? Okay, now what would happen? So what whenever we randomize these strategies, he would not let A to stick with a specific strategy. So basically that means the choice of alpha would allow the reward coming from playing P for A and playing Q for A are the same. So basically the randomizing over to the two action would not give us any like more benefit. In this regard, the choices of alpha of B should be selected in this manner. With this given, we are going to end up with the equality of 3 alpha by 2. It says alpha should be 1 over 3. Due to the symmetry, I would say you can easily say A would follow the same mix randomization. In that case, you can calculate the mix Nash equilibrium should be playing P with 1 over 3 probability for both, and the expected reward is R. Okay, let's move for 2 exercises. I recommend you to try first, then check the results. So we consider here, we consider 3 transmitters accessing 2 mediums given different rewards. So the medium 1 can be accessed by only 1 at a time, where medium 2 can be accessed at most by 2. So in this case, I'll consider 3 transmitters as A, B, and C. And if we consider A transmitter using accessing medium 1, and we will try to see what happened to B and C whenever they try to access mediums 1 and 2. 1 and 2. So basically here it means collisions, no rewards, accessing 1, of course, no reward for B, none for A, but C is accessing 2, he has a reward. Here, no reward for A and C, while B is accessing 2. While here, reward of 2, because he is the only one, while others are accessing medium 2. Now, when we consider A is accessing the medium 2, we can go for the same table. Okay, here 1 and 1 via B and C collide, but A is getting a reward. Here, let's say B is sharing with A. C is getting the reward. Here B accessing 1 and C is sharing, while here 3 are sharing, so means no reward bearing as well. Now to find the Nash, of course, yeah, here easily we can say this is not Nash. We can move here, and when we add here, so we can decide to move here, but when we are at this point, neither B changes, C changes, no, A changes this strategy. So this is going to be a Nash, this one, and similar this one. Now, if we think about the Pareto optimality, where deviating means no harm to others. So from here, he can deviate, C can deviate, no harm to others. From here, he can deviate, no harm, and A doesn't want to change. So this is Pareto optimal. And from here, basically that means, okay, these 3 are Pareto optimal, but and these, none of the others are Pareto optimal. So these Nash are also going to be same as Pareto optimal. Now we ask to assume the homogeneity among the transmitters and find the mixed strategy Nash equilibrium. So that means all access medium 1 with probability alpha, while the second medium with probability 1 minus alpha. So if I write how A sees how others are accessing, so B and C access both medium 1, so this is a chance of alpha square, and accessing medium 2 with this, and 1 and 2 with these probability. So basically this is the marginal probability distribution, which I discussed earlier in a slide. So now if you consider about the payoff of A using the medium 1, you can see, okay, it happens only here, right? He is getting only 1 minus alpha square times, okay, 2. Yes, it's 2. Then when he uses 2, he gets 1, 1, 1 here, all three cases. So we know since it's a marginal distribution or summation would be 1, so we can easily say this is 1 minus alpha square. For the sake of simplicity, I'll write this. So at the equilibrium, what happened? The choice of alpha makes no difference of choosing one of these two utilities. So basically we need this equals this. That considers Nash. Correspondingly, we can end up with 1 minus alpha square equal to 1 over 3, right? Alpha should be 1 over root 3, right? So you can calculate a corresponding reward based on this. So this is the mixed strategy Nash. Then the question asks to extend this scenario for n transmitters. Only the change is when sharing the medium, accessing the shared medium by all results no, but otherwise it is 1. So we can extend the previous results in this case. Let's say here using 1, you get reward 2 only when nobody else access medium 1. Then when a transmitter access medium 2, he get rewards for all the time except everybody access the medium 2, right? So this is the everyone else accessing medium 2 except this case, he is getting a reward of 1. So here for Nash equilibrium, what we need, UA1 equals UA2. That corresponds to, if we follow the same steps as last time, it should be 1 minus 1 over 3, 1 n minus 1. Now the next question is about, okay, what is going to happen when n goes to infinity? So we can say this is this alpha n. So we can say alpha infinity could be 1 minus limit n goes to infinity 1 over n minus 1. Yes, this goes to 0, this goes to 1, this goes to 0. So basically this becomes 0, right? So that means there's no chance that they can access to the shared one. So basically this means what you can tell about the utility. So this is also going to be 0 because with an infinite number of transmitters, there is a high chance they are going to collide with each other. To avoid that, they try to access the medium 2. So basically they collide again, right? So that is the result. Now let's consider about a case where about, okay, whether to reveal the attributes. For this example, we consider 3 transmitters that has access to the same channel. So the rule is only one can use the channel at a time. So therefore they have to decide, okay, who will be using the channel. So in a randomly selected order, so each transmitter decide to attack some their opponents, one of their opponents, and block it. So they have like 3 different strengths. So A can decide to attack somebody and block it with 100% probability. B can decide to attack but only can block with 50% probability, and C can do it only by 20% probability. Once a transmitter is blocked, he has no longer access to the channel, and the last man standing will be the one who is accessing channel. So let's say if it is the order is A, B, and C. So and if A decide to attack B, B is out of the game, and then C decide to attack A. If C success, C will get the chance to access channels. If he fails, then turn gets to A is going to attack C, and A gets the access. Now here we consider two different strategies. First one, when these attributes, these strengths are unknown, what naturally do, everybody attack a random opponent. So in this case, if this is order, A can either pick B or C. If this is the order, B can decide to pick A or C. The second approach we are considering, attacking when these attributes are revealed, everybody decide to attack the most powerful one who has the higher chance to attack and success. So if we take the same example, A is definitely going to attack B because he is the one posing the threat to him if he remains. And both B and C prefer to attack A. Sorry. Okay, now you can work out and see what are the values, but let's say this I have a couple of values ready beforehand. So try to make sure you do it and size the value, but I just want to give the idea here. So when you pick the random opponent to attack, you can find that after all possible order of attacking, if you take the expectation over it, A is going to remain with 44% probability, B is 33, and C 23. So basically the strongest or highest capable in terms of blocking others or successfully attacking is going to be the most successful transmitter. But now what happens if the attributes are revealed? Then what could happen is whenever I get the chance, A is try to take over B, then C, and B and C both try to take A out of the picture. Based on that, what we got is, I think there was a mistake in these two steps, you can find out, but this will be 7-5, and this will be 7-5, and this will be 2-5, and this will be 2-5. Basically, this will be like 1/3 of 28, maybe roughly around 32. This will go slightly about 38. Just unsure based on these changes. So what we could see, the one with highest capability is not going to win anymore. The one is the weakest capability is going to be more successful because these two, this A is going to attack B whenever he gets a chance, and both B and C, they join forces to attack A. So the strongest ones are likely to be killed first, and the weakest one is going to last on average. That says maybe in some cases it is not better not to reveal the attributes. Usually in a game, the one with the strongest abilities, they might prefer to stay like keep their attributes private as long as they get the upper hand. Otherwise, as we know, all other players get together and start to attack the one who has the most likely to win, and he's going to suffer, right? Then the weakest guy going to prevail. Okay, that's all for this tutorial, and see you next week. Thank you.